Hi there. During this session I'm going to try and talk about free body diagrams. These are diagrams when the body is considered free of its surroundings and only the forces acting on it are shown. So let's go through some examples and try and highlight the main features, okay? So here we've got an astronaut using a jetpack to push a satellite. Okay. The physical picture shows the action, and we can see the force being applied by the astronaut. Now the free body diagram of the satellite will just show a force coming from, as modelled from a point, and the tail of the vector always originates from that point source. So that's an important feature. So from the point source the forces are moving in that direction. Okay, so that's the one force acting on that satellite. We know that weight acts vertically downwards towards the centre of the Earth. So what we have here is we recognise that the physical picture, we've got mass and we know that there's going to be weight existing in it, but our free body diagram would just have weight coming from the centre of mass. Also note, it's really important and quite convenient to make sure you pick a suitable X and Y axis to try and help you working out some of the components in more complicated situations. The next example. So, we're going for some more forces now. In this case we can see a fireman sliding down a pole. Okay. The fact he's sliding down that pole, in fact, is we look at the forces. There's the force of friction and the weight. Now in this case it's great to see because we can see that the weight is greater than the force of friction, so therefore it's imbalanced. So we can also ascertain from this diagram that the fireman is accelerating down the pole. Okay, now we're thinking about a book which is resting on a hand. We can see the physical picture. Now if we think about the forces acting on it, we've got the force of the hand pushing up, and then we have the weight of the book pushing down again. Now please notice, and we're going to talk about this later on, this is not an action-reaction pair because they're different forces. And we'll talk about action-reaction pairs when we talk about Newton's laws later on. It's just a note for you to think ahead. So we've got Jack and Jill going up the hill now. This is where I can really emphasise the importance of recognising where your Y and X axis are going to be located. What we have in the physical picture, we have a force due to Jack and a force due to Jill going off at different angles, and then we have the weight going down again. Now in this free body diagram we can mark this off with all the forces acting from the central point, and if the situation was that the pail of water wasn't moving in any way or was moving at a constant velocity, that means all these forces would have to cancel out, and so therefore we could probably work out the angle there by looking at the vector components if required. And that's why picking a suitable X and Y axis is so important for these types of questions. Here we have an ice block, so another situation. Now in this case we have the weight pushing down, and we also have two other people providing forces which are pushing down, and what we have is, in response to those forces coming down, we have the normal. Okay, so it's not a force pushing upwards, but it's a response from the objects below, therefore causing all the forces to eventually balance out if we look at all the components, because the ice block is not moving at this moment in time. But again, picking the right X and Y components will be very, very useful in this situation. Now, this normal is a contact force, so it's a response to contact with another object. Now just remember that this is not the contact force of the ground of an object is always at 90 degrees to the surface. Okay. But that surface may not be 90 degrees to what we are expecting. For instance, in this case we have a snowboarder coming down a mountain. Now, to help the calculations here, if we set our y and x axis at 90 degrees to the normal, and the x-axis is parallel to the surface, it makes our calculations come up much more easily when we do some more work on that. There may well be some other forces acting here. For instance, there could be air resistance, but we're just trying to emphasize the fact that the normal force is always going to be at right angles to the surface, and it's that contact force. Sometimes it's known as the reaction force. So let's consider, kind of extend this idea. So let's think of a sledge going down a slope. Now in this case what we have here is we have two forces acting on it. We have the contact force and we have the weight. Okay. If those are the only two forces acting on it, what we can do is we can work out and look at some values and recognize that the x and the y components of the weight are going to be able to help us solve some problems. So in this case what we can see is that the y component of the weight should be equal to the contact force, and it's actually the x component of the weight which is providing the acceleration. So this young man is accelerating down a hill. So again, it's really useful to make sure we pick a sensible coordinate system. I'm going to mention tension here. Tension is a force that often comes up. I'm just kind of mentioning it as to how to handle it. Tension is the force of a string or spring that is pulling on an object. Now, we've got to remember the direction of tension force is always away from the surface of the object to which the rope is attached, and that tension is equal in every position along the length. So if we have a pulley and we have a tension in the rope going away from the bucket, that tension is going to be equal on the other side of the pulley. If we have two bits of rope wrapped around, then what we have is we have an equal tension in both these bits of rope away from the bucket. So tension force is a force I'm just mentioning there, kind of out of the context of free body diagrams. So let's think about some problems now. If we draw a free body diagram, can you find the acceleration of the sled if the mass of sledge M is 20 kilograms and the force F is 20 newtons and the angle is 30 degrees? So think about that. Again, what we need to do here is find out what the x component is of the force. So that would be 20 cosine 30 degrees divided by the mass is going to give me the acceleration, which is 0.87 meters per second squared. Another situation here, draw a free body diagram and determine what value of F keeps the correct motion. Okay, so we're looking for an unknown value here of F. Now what we're really doing is we wanted this to be travelling in a straight line, and so therefore we need to recognise that F cos 45 is going to have to be equal to 130 sine 34. Okay. So that means that we can find out that the force is going to be 103 newtons. Another example here to work on. A free body diagram to determine if the little kid and the sled together have a mass of 50 kilograms, what the acceleration of the sled is. Okay, so here we can see a bunch of forces taking place. We've got 55 newtons and 55 newtons, and we've got a frictional force of 57 newtons. So if we do a free body diagram, we've got to recognise that the net force in the direction of the acceleration is going to be 55 cos 35 degrees plus 55 cos 35 degrees. So that's the force in the forward direction here, minus 57 degrees gives me a total force of 33 newtons in the direction of the acceleration. If it's 50 kilograms and I know what the force is, you can tell me that this young man should be accelerating at 0.66 meters per second squared.